Rotational kinetic energy is actually not that bad. It sounds really scary, but it actually is super straightforward. It's basically just like our energy unit, but now we're just going to throw in another equation for you, but it's really the same equation. So the torque unit itself is super complicated, but this part of it I find to be super straightforward. So let's take a look at it. So translational kinetic energy over here is just 1/2 mv squared. And anytime you have something moving or slipping or sliding, you're going to have translational kinetic energy. And so far, that's the only thing that we've talked about. But now we're going to also add on to that rotational kinetic energy. And so this is the equation for rotational kinetic energy. And it's going to be any time that something is rolling, rotating without slipping, or just rotating in general. So anytime you have something going in a circle, then you're going to have rotational kinetic energy. And the reason why I say that this is really the same equation here, you've got kinetic energy before with nothing here. And now you just have kinetic energy and it's specified that it's in rotation. The 1/2 is the same. Just like everything else, instead of mass, we're going to have moment of inertia, because moment of inertia is not just how much mass it is, but also where that mass is compared to where it's rotating. Because it's much easier to fling a ruler around if you hold it in the middle versus if you hold it at the end. And then the velocity squared, when we talk about translational, it's just normal velocity. When we talk about something rotating, now it's angular velocity. So it really is exactly the same equation. Translational kinetic energy, this is just an example of that. You're going to have a cart rolling down a hill. And so a lot of times you'll notice, and especially going back, you'll notice that you had like a box or a block or a car going down a hill. And now what you're going to notice is that we are going to have something rolling down the hill. So something that is rolling, it needs to actually rotate and move. And so in this part of the unit, you are going to have something rotating and moving. And so this is rolling without slipping. Slipping would be like if it's skidding across but not rotating. And almost all the time, you're going to have rolling without slipping. If you have only rotational kinetic energy, this is going to be something that's rotating but not moving. So if you're burning out your tires, your car's not moving, but your tires are rotating. You have a pulley rotating, but it's not moving anywhere, like it's attached to this well. And so this piece is going to rotate but not go anywhere. This top is spinning. It's not going anywhere, but it's rotating, so it will have rotational kinetic energy. So, how do I deal with a problem where I have a ball at the top and it's rolling down to the bottom? Well, the easiest way to do that is by using conservation of energy. And so, I want to think about what energy do you have at the top, what energy you have at the bottom, and how are translational and rotational kinetic energies related to each other. So, think about that for a moment, and then I'll go on. So I'm going to do an energy bar chart just like I've done before. If you are unfamiliar with these, go back and look at my energy unit and how I explain how energy bar charts work. So up here at the top, this ball is not moving, or this could be a cylinder or a can of soup or a soda can. It's sitting up here at the top. It has some radius, whatever it is, some mass, who knows what. And I'm going to let it go and it's going to roll down the hill. And so as it rolls down the hill, it's going to get faster and faster. But at the very top, I'm going to say for the moment, it's not moving. So that means that I'm going to be up in the air, which means I have gravitational potential energy. Translational kinetic energy, it's not moving. So that'll be 0. Rotational kinetic energy, it's also not rolling. So that'll be 0. And the work done is 0 because here it says assume the loss due to friction is insignificant. So that'll also be 0. All right. So then what about at the bottom of this hill? So at the bottom of this hill, I'm going to have a gravitational potential energy of 0 because it's going to be at a height of 0. So when I'm thinking mass times g times my height will be 0. So that'll be 0. My translational kinetic energy, that's because it's moving like side to side, that I will have some. And then I'm also going to have rotational kinetic energy because this thing is going to be rolling down the hill. And I don't care right now which bar is bigger or if you make them the same. The main thing is that when I add these two together over here, I'm going to end up with the same stuff as on the left. So remember that when I add up all of this stuff on the left-hand side, it needs to be equal to the stuff on the right-hand side. And this gravitational potential energy is 0. And then I have that. So I'm going to be able to figure these out. But the issue is I don't know my velocity at the bottom. And I don't know my angular velocity or my translational velocity. So I need to remember, okay, how do I deal with that? Well, if you remember, my rotational kinetic energy, my rotational stuff versus my translational stuff, if this is my radius and this is my angle, radius times my angle is equal to how much it rotates. Here it's labeled L. Usually you'll see it labeled X. And if you're in calculus, you'll see it labeled as S for the arc length. The one thing that we're going to be noticing here, though, or using a lot, is that velocity is equal to your radius times your angular velocity. So we've already taken a look at that. So now, remembering that, I'm going to go back and plug this in. And so I'm just putting in my equations for each of these. So gravitational potential energy is mgh. This is 0 still, so 0. That's still 0. This is 0. And then over here, gravitational potential energy, oh, this is going to be 0 at the bottom. And then kinetic energy is 1/2 mv squared. Rotational kinetic energy is 1/2 my moment of inertia times my angular velocity squared. So we're going to start from our general equations for each of these, and then I'm going to show you two different ways to do this. So if I wanted to solve for this angular velocity at the bottom, then it would make sense for me to put both of these in terms of angular velocity. Well, we just said that velocity is equal to r times my angular velocity. So what I'm going to do is I'm going to substitute that in. So instead of velocity right here, I'm going to put in r times, or my radius times my angular velocity. And then uh, the place that everybody makes a mistake is this next part. So they'll remember to put in r times my angular velocity, but then what they'll forget to do is that that squared distributes in. So you're going to end up with r squared times your angular velocity squared, which if you have numbers, it usually isn't a problem. But if you're dealing with variables, then that's when students tend to mess that up and make mistakes. So just be really careful with this part. It's the most common spot to make a mistake there. But what if you don't care about angular velocity? What if you want to know how fast the ball is moving in terms of its translational velocity? Well, in that case, I'm going to rewrite this equation as and just divide both sides by r, and then I get my angular velocity is equal to velocity divided by r. So I'm going to start with that first equation again, the same way it was before. And now instead of my angular velocity, I want to get a velocity in there. And so what I'm going to do is I'm going to substitute in and put uh, my velocity divided by r instead of my angular velocity. And then again, this is the other spot where people mess up, is they forget to distribute this squared in. So you're going to end up with v squared over r squared. So be really careful about this part when you go to substitute numbers in, that squared is not getting lost, because that's the number one way to get a wrong answer on this. All right. But besides that, that's all there is to it. Then all you need to do is plug in the numbers and do some algebra, and you'll be able to solve your uh, rotational and translational conservation of energy type problems. Take a look at the examples and the example videos to see how this really plays out. Otherwise, I'm going to go on to one last thing, and that's this relationship between translational work and rotational work. They really are, again, the same thing. Work is work. That's going to be your change in energy. And when we talk about translational, we were dealing with force. But when we talk about rotational, it's not just force, but where you apply the force that matters. So we're going to use torque. Instead of distance, we need to talk about how much angle that it went through when you were applying the force. So it's really just take the linear stuff, find the angular equivalent, plug it in, and that's all there is to it. And then force, of course, is ma. When you talk about net force being equal to mass times acceleration, so that's where that comes from. And then torque, when you do a net torque equation, it's equal to moment of inertia times your angular acceleration. So assuming there's only one force or assuming there's only one torque, then this is a really simple way to do it. Otherwise, be careful. You really do need to do those net force and net torque equations. When you talk about power, again, same thing. Power is work divided by time, or it's your change in energy divided by time, because work and change in energy are equal to each other. So I went ahead and underlined work in pink. So hopefully this makes sense. So work is force times distance. So instead of work divided by time, I'm going to have force times distance divided by time. And then over here in the angular land, work is still work. But when we're talking about work in an angular type situation where things are rotating, I'm going to put in torque times my change in angle, and so that's going to go in here. And really, this is your torque times your change in angle. This is your force times your change in distance. But a lot of times I feel like that just makes this look more complicated than it really is.
So the last piece of this is then simplifying it. So you'll notice here that I have velocity is equal to distance divided by time, and really it's your change in distance divided by time. But that is also incorporated into this power equation. I've highlighted that in blue. And so then in terms of power, you can then simplify this to force times your velocity. And the same thing can be done for rotational power when you're talking about things rotating. Is angular velocity is this change in your angle divided by your change in time, which is included in this part here, also in blue, which is just your angular velocity. And that's all there is to this.